Title of the radio-enabled learning course is Advanced Material Science. In this course, we will discuss and know about ceramics and composites, polymers, dielectrics, electronic materials, magnetic materials. First of all, I will introduce about what is material science. Material science is something that consists of matter. Advances in technology depend increasingly on the development of better materials of greater strength, lightness, safety, electrical conductivity, resistance to corrosion, and resistance to heat. This is especially true of those industries engaged in aircraft production, space projects, telecommunications, computer manufacture, and nuclear power engineering. Structural materials are required to be stronger, stiffer, and lighter than existing one. In some of cases, they may have to withstand high temperatures or exposure to intense radioactivity. Materials with very precious electrical, magnetic, thermal, optical, or chemical properties are also demanded. The comparatively new subject of material science is concerned with the study of materials as a whole and not just with their physical, chemical, or engineering properties. Material science attempts to relate the properties of materials with their structure at the electronic, atomic, and micro level. It is an interdisciplinary subject. The concept of material science covered a wide range of topics, as well as asking how materials behave. The materials scientist also wants to know why they behave as they do. Why is steel strong, glass brittle, and rubber extendable? To begin to find answer to such questions as required the drawing together of ideas from physics, chemistry, metallurgy, and other disciplinaries. The deeper understanding of materials which we now have has come from realizing that the properties of matter in bulk depend largely on the way of atoms are arranged when they are close together. Material science is a rapidly advancing subject with exciting prospects for the future. Its importance lies in the help it can give with the selection of materials for particular application, with the design of new materials, and with the improvement of existing one. From this introduction, we move on to Unit 1, Ceramics and Composites. Objectives of this unit: to know and get deep knowledge about structural features of ceramics and composites, production of ceramics, forming and post-forming process of ceramics and composites, mechanical properties, commercial ceramic system, silicon aluminum system, technical ceramics, and zirconium and silicon alloys, and also know about cement and concrete, composite material, continuous and discontinuous fiber composites. In the first unit, we will see and discuss about ceramics. The word ceramic is originated from Greek word keromikos, which means brutant stuff. Ceramics are compounds of metallic and non-metallic elements. Characteristics of ceramics are high temperature stability, high hardness, brittleness, high mechanical strength, low elongation under application of stress, low thermal and electrical conductivities. Ceramics are classified in many ways. It is due to divergence in composition, properties, and application. Based on their composition, ceramics are classified into oxides, carbides, nitrides, sulfides, fluorides, etc. Based on the specific application, ceramics are classified as glasses, clay products, refractories, cements, advanced ceramics for special application. Based on their engineering applications, ceramics are classified into two groups: traditional and engineering ceramics. Traditional ceramics are mostly made up of clay, silica and feldspar. Engineering ceramics these consist of highly purified aluminum oxide, silicon carbide and silicon nitride. Then we will move on to introduction to processing ceramics. The very specific character of ceramic is highly temperature stability and makes conventional fabrication routes unsuitable for ceramic processing. Inorganic glasses make use of lower melting temperatures. Most other ceramic products are manufactured through powder processing technique. Typical ceramic processing route: powder synthesis, green component, that means compacting, casting, like that, and also sintering and firing. Next we will move on to processing ceramics. In this processing ceramics we will see glasses. Most of them are silica soda lime variety. Raw material are heated to an elevated temperature where melting occurs. Glass melt is processed by different technique to form different products. Example, pressing techniques means to form shape like plates and dishes. Blowing technique means used to produce objects like jars, bottles, light bulbs, etc. Drawing technique, that means to form lengthier objects like tubes, rods, etc. Next we move on to ceramic powder processing. Ceramic powder processing is used to synthesis of powder followed by fabrication of green products, which is then consolidated to obtain the final product. Synthesis of powder involves crushing, grinding, separating impurities, etc. Green component can be manufactured in different ways. Example, tape casting, slip casting, injection molding and cold hard compacting. Green component is then fired or sintered to get the final good quality product. Slurry of ceramic powder is processed via casting technique like tape casting and slip casting. First we will discuss about tape casting. Tape casting, also known as detector blade process, used for making thin ceramic tapes. In this slurry of ceramic powder, blinders, plasticizers is spread over plastic substrate. Tape is then dried using hot air. Later, tape is subjected to binder, burnout and sintering. Next, we should know about slip casting. Here, aqueous slurry of ceramic powder is poured into plaster of Paris mold. As water begins to move out due to capillary action, thick mass builds along mold wall. It is possible to form solid piece by pouring more slurry. In this ceramic powder processing, we also know about extraction and injection molding. Extraction: viscous mixture of ceramic particles, binder and other additives is fed through an extractor where continuously shape of green ceramic is produced. Then the product is dried and sintered. Then next we will know about injection molding. It is similar to the process used for polymer processing. Mixture of ceramic powder, plasticizer, thermoplastic polymer and additives is injected into die with use of extractor. Then polymer is burned off before sintering rest of the ceramic shape. It is suitable for producing complex shapes. Extraction and injection molding are used to make ceramic tubes, bricks and tiles. In the ceramic powder processing, we will see about compaction. Ceramic powder is compacted to form green shapes of sufficient strength to handle and to machine. Basis of compaction: application of external pressure from all directions. In cold isostatic pressing, that is known as CIP. In the CIP process, pressure is applied using oil or fluid, then green products is subjected to sintering. In hot isostatic pressing, it is well known as HIP. In the HIP processing, pressure is applied at high temperature, thus compaction and sintering occurs simultaneously. It is expansive but have certain advantages. In HIP is used as when during CIP not enough strength is gained. Almost nil porosity is requirement for refractories and covalently bonded ceramics. Next, we will see about sintering. In this process of subjecting the green ceramic to elevated temperatures with the purpose of gaining mechanical integrity. Driving force for sintering is reduction in total surface area, thus energy. Diffusion, that means atomic and bulk, is responsible for growth of bonds at contact points of particles like necks. These are the important things to know production of ceramics. Next, forming of clay. All clays will be lubricated by addition of water. Improves plasticity too much and will become unworkable. Clay platelets separated by water molecules and held by H bonding. Bond will shear if force applied but has enough strength to retain from at rest. Too much of water, then platelets become too separated. Move to dispersion. If this is stable, can form a slip thick creamy dispersion. Drying and firing clay. Drying evaporates excess water. Platelets move closer together, allows direct H bonding between hydroxyl groups. Known as leather hard stage, clay can still be recovered to plastic state by reintroduction of water. Ceramic can be majorly classified as oxidic ceramic, non-oxidic ceramic. Oxidic ceramic can be classified by two types. One is silicon ceramic, another one is metal oxide ceramics. Synthesis ceramic raw materials. Silicates. Depending on the charge, natural raw materials may show slightly differing chemical compositions or different grain size distribution. This makes processing in manufacturing plants occasionally difficult, and this is the reason for experiment to produce silicates synthetically. For the production of synthetic silicate, that means SiO2 is hydrothermically solubilized with caustic soda This leads to an aqueous water glass solution which is spray dried. The result is an amorphous disilicate which after further dewatering is transformed to a crystalline disilicate. The crystal structure consists of tetrahedron and octahedron layers with water in the inner layers, just like the natural layer silicates. As these synthetic silicates are stirred in water, calcium ion from the water get integrated into the inner layer and the water is softened. Compared to the natural layer silicates, the pureness of this synthetic material is an advantage. The content of alumina and silica is comparable, but there are clear difference with regard to the iron content, which is particularly responsible for the raw material discoloration. Oxides. All oxides of periodical table element belong to ceramic materials. All selection of most important oxides which are very attractive due to their field of application. Among them we find beryllium oxide, magnesium oxide, calcium oxide, alumina, yttria, zirconia, as well as thorium oxide, which have extremely high melting temperature. Ceramic oxide materials are characterized by their ionic bond and therefore show no electronic conductivity. This explains the high specific electrical resistance. Then non-oxide materials. Non-oxide ceramic materials comprise the elements silicon, nitrogen, carbon, boron and aluminium. The chemical compounds herein are Bn, Si3N4, Aln, SiC, B4C, SiB4. The elements of which the mentioned compounds results stand within the periodic table are relatively far to the right. This means that there are electronic configuration in the outer orbital has been already relatively completed. Therefore, the different elements provide each other with electrons for covalent bonds without electronic conductivity. What is a typical characteristics of the ceramic material? Further left on the periodic table, the elements like titanium, zircon, which also form carbides which carbon or nitrides with nitrogen can be found. Due to the presence of metallic bonds and their electronic conductivity, they are no far considered as ceramics. Structure of SiO4. Tetrahedra are linked to sheet or belt silicate. They also have negative charge. To become electrically neutral, cations or other positively charged structural components have to attach. Layer silicates, for example, when the tetrahedron layer links to an octahedron layer consisting of aluminum oxide and OH groups. This construct is called double single layer because within stacking sequence every third layer shows the same geometrical array as the first layer. In the lower section where the three oxygen ions are situated, the tetrahedron layers has a negative excess charge, and in the upper section where just one oxygen ion above the 4 valence free silicon ion is found, a positive excess charge. This positive excess charge in the upper part of the SiO4 tetrahedron are saturated as the octahedron layer with negative excess charge attached to the SiO4 tetrahedron. With regard to 3-layer minerals, a tetrahedron layer attaches to both the top and the bottom of the octahedron layer. These layered minerals form the basis of clays, which in the following reviewed in detail. Water molecules can intercalate between the layers. This intercalation of water molecules influences enormously the processing property of clay. Water molecules are attached by hydrogen bonds to the oxygen ion or OH group of each layer. In case of shear stress, this slight bond causes the layers shifting against each other, and this leads to certain plasticity used for plastic forming. Exchange of silicon atoms in tetrahedron layers or aluminum atom in octahedron layers bring about a variety of minerals. If a 4-valence free silicon ion is replaced by a 3-valence free aluminum ion, a cation in the interlayer ensures valence equalization. This cation is highly flexible in the liquid layer and can very easily be exchanged. Here we talk about ion exchange capability. This exchange capability can, for example, be used for water softening, as we will see later on. Anions can also be light in or be exchanged if the 4-valence free silicon ion is replaced by a 5-valence free ion. In addition, the number of water molecules can be varied in the inner layer. If air humidity changes from 90% to 96%, 96% to 99%, the clay minerals absorb more water. Water content increases from 0.4 gram water per gram dry substance at 90% relative humidity up to 1 gram water per gram dry substance at relative humidity of 99%. If humidity increases, the layer distance also increases. Water leads to a chance of processing property of these materials. As already mentioned, free cation are often exchanged in tetrahedra or octahedral, silicon ion in tetrahedron layer, aluminum ions in octahedron layers. The variety of minerals which can be found in nature is symmetrically summarized. Mixture of all these minerals can also be found in the nature, making their analysis. If 3-valence free aluminum atoms occupy 2 octohedra each and the third octohedron remains empty, this layer's success is called dioctohedral. Then we will see about mineral names and its crystal system. First, forsterite, the name of mineral. The crystal system is orthorhombic. Fialite belongs to orthorhombic crystal system. Zircon belongs to tetragonal system. The mineral name is kyanite. Belongs to triclinic crystal system. The mineral name is mullite. Belongs to orthorhombic crystal system. The mineral name is sillimanite. Belongs to orthorhombic crystal system. The mineral name is enstatite. Belongs to orthorhombic crystal system. The mineral name is proton enstatite. Belongs to orthorhombic crystal system. Mg2SiO4 mineral is having tetrahedron crystal system. BaTiSi3O9 belongs to rings crystal system. Al2Be3Si5O18 belongs to 3-fold ring single, 6-fold ring single, 6-fold ring double shape. MgSiO3 is chain single double shape. Al4Si4O10OH8 is single sheet like shape. SiO2 is framework 3-dimensional system. different types of ceramic having different types of crystal system and structural like hexagonal, orthorhombic, triclinic, cubic hexagonal, orthorhombic, monoclinic, triagonal, hexagonal, etc. Each ceramic system having its own properties. Ceramics contain the same imperfection in their crystal structure as metals like vacancies, displaced atoms, and microscopic cracks. Glass, a state of matter as well as a type of ceramics. As a state of matter, the term refers to an amorphous, that means non-crystalline structure of the solid material. The glassy state occurs in a material when insufficient time is allowed during cooling from the molten state for the crystalline structure to form. As a type of ceramic, glass is an inorganic non-metallic compound or mixture of compound that cools to rigid condition without crystallizing. Next, why so much SiO2 in glass? Because SiO2 is the best glass former. Silica is the main compound in glass products, usually comprising 50% to 75% of total chemistry. It naturally transforms into a glassy state upon cooling from the liquid, whereas most ceramic crystallize upon solidification. Some of the advantages of glass ceramics: efficiency of processing in the glassy state, close dimensional control over final product shape, good mechanical and physical properties, high strength, that means stronger than glass, absence of porosity, low thermal expansion, high resistance to thermal shock. Application: cookware, heat exchanger, missiles, etc. Greatest amounts in manufacturing are in ceramic compound, SiO2 in glass and silicates in clays, and alloying elements in steel, aluminum and copper, also used as a reduction agent in certain metallurgical process. Significantly technological important is pure silicon as the base material in semiconductor manufacturing in electronics industries. The vast majority of integrated circuits produced today are made from silicon ores. Advantage of ceramics: run at higher temperature, excellent corrosion resistance, low frictional losses, ability to separate without a cooling system, low density. The major disadvantage is brittleness, too easy to have voids, weaken the engine, difficult to machine. Advantages in electronic packaging: chosen to securely hold microelectronic and provide heat transfer, must match the thermal expansion coefficient of the microelectronic chip and the electronic packaging material. Additional requirement included: good heat transfer coefficient, poor electrical conductivity. Material currently used include boron nitride, silicon carbide, aluminum nitride. Thermal conductivity 10 times that of alumina. Good expansion match with Si, silica. So dear students, in this episode we discussed about structural features of ceramics and production of ceramics and forming and post-forming process of ceramics. Thank you students. We will discuss the new topic in Unit 1 in the next episode. Thank you.